Thank you very much, it is a pleasure to take you through in a relatively short 10 minutes, 18 odd years worth of development and about another 10 years previous to that of technology development to get hydrogen fuel cell technology into products and into markets and into consumer hands and user hands. There have been a whole lot of challenges along the way, but the breadth and gamut of the technologies and the way in which they are applied in different areas have been split essentially across Intelligent Energy's open cathode PEM fuel cell systems. We've only worked on PEM, not worked on any other fuel cell systems, and closed cathode. So in the context of smaller power systems, air-cooled open cathode from two wheels, you've seen the fuel cell motorbike, currently in police colours at the front. That's development that was done in conjunction with Suzuki, and then through the IE Suzuki joint company, the Smile. We've done personal portable fuel cells, telecom towers in India. We're working on drones now. We've got backup lighting and so on. Larger fuel cell systems in a wider range of motive types of applications. But you can use fuel cells in a wide variety of ways, but these have been either stationary. Aerospace has been a fairly significant activity for us over the years, and keeping in that tradition, working with drones since then. But these are systems then between the smaller and through to the larger. You're looking at a distinction between something that is around a few watts right the way up to a little over 100 kilowatts of power, usable for whatever format of the system is required. Hydrogen. We have used and continue to use a lot of hydrogen. And that is, but to some extent, been one of the challenges, because if you're doing fuel cell systems, the whole concept of being able to get them into the hands of customers means that you have to have proven them, shown that they're durable, safe, perform. You know what the failure modes are, you know how to control, you know how to correct, you know how to deal with the worst environment that a fuel cell wants to be in, which is very low relative humidity, whether it's hot or cold, or in very, very cold temperatures. We've got a lot of test stations, we've got a lot of production facilities, all of which need hydrogen, and the hydrogen is supplied on our site via the BOC Linde Group from UK sources, SMR typically. It's a challenge that has been taken into the context of manageability as well, because all of that has, over the years, with using potentially, when you've got 100 kilowatts of fuel cell on test, plus lots of smaller systems on 24-hour running 7 days a week, you're talking about half a ton of hydrogen potentially a week that you're consuming. So knowing for ourselves what we're doing with the hydrogen and how you manage it and how you do that safely has also been part of our challenge. And that challenge has been to get the application-specific requirement framed so that it works at point of use in terms of operability and performance. So while we do not do hydrogen, we do have to work with hydrogen storage, hydrogen integration, cylinders, different cylinder sizes, pressure regulation, and the like. And in this particular case, with the drones that we work on today, you also have to look at where you site these in the particular platform that you're working with in order to optimize the positioning of the fuel cell system and the hydrogen storage. We bring the hydrogen cylinders into the supply chain for the operation. We make them available initially with customers, and we can do that in, as you can see, different configurations, and also for fixed wing applications. We started off as an alternative area around the two-wheel side with concerns about hydrogen availability. That's a challenge that's referenced now. It was an even bigger challenge back in 2005 when we first approached this. to come up with a clean sheet design for a fuel cell vehicle, a zero-emission personal transport application. And the response was, you create a cartridge, a swappable cartridge. You can take, or you can have a supply chain of swappable cartridges. You don't have to necessarily take the vehicle to the hydrogen storage and refueling location. So you can create alternative supply chains. I'll come back to that point later. When it came to the decisions with Suzuki, their view was you want the maximum amount of hydrogen on board. You want to integrate it safely, securely. You don't want to interfere with that cylinder. Essentially, once it's in place, it's usable for the life of the vehicle. So that is a fixed cylinder, future-proofed in their view at 700 bar. So the vehicle that's in the atrium there has 700 bar hydrogen as the storage system. Moving it on to four-wheel applications, we also, in conjunction, for example, and these are all just examples, we've done lots of other things that are in the background. This was another example where Peugeot Citroën, that we worked with back in 2008, 2009, also had the view that the hydrogen availability, network availability is something that you don't try and assume is going to be ubiquitous. Assume that there will be areas where you're not able to get to the hydrogen. Again, create a removable tray with the hydrogen storage, and you can have a supply chain that works around that as well. So you're not necessarily relying just on hydrogen refueling stations. When we started to develop the fuel cell taxi, that was back in 2009, 10, we were looking at how to optimize the amount of hydrogen against a duty cycle. We knew what the average taxi duty cycle was. We knew how the drivers, where they approached, how they approached operation during the day, when it's convenient to be able to refuel and so on. And that was configured around a daily duty cycle and a weekly duty cycle in order to manage with only 2 refills during the week. Those, of course, were configured and were to be operated in conjunction with fixed infrastructure. Not all taxis are back-to-base vehicles. It's been talked before that a lot of public service vehicles are back-to-base, and that significantly, and it really does significantly, reduce the network effect that is required. But you still have the issues that where you need to be at any one time and in configuration with the availability of the hydrogen for the refueling station replenishment. That can be the challenge, not necessarily whether you can get your vehicle there. So there are still plenty of challenges in that sense. You can look out into the fact that there are hydrogen refueling station facilities developing across Europe, around London, and in the United States, elsewhere. These will often, and increasingly, in the example of the M25 in London and around in Germany, you are using fixed infrastructure that's already there because they're part of the hydrogen refueling network anyway. So it's not necessarily having to go out and find a greenfield site. You can co-locate, and that is going to be one of the answers. This is the UKH to mobility plans perspective in terms of how HRS networks get rolled out. I need to emphasize that that is purely developed in conjunction with refueling passenger vehicles. When UKH to mobility went through its first stage of planning and forecasting the roadmap and what was going to be needed for the vehicle rollout and support for those vehicles, it was just on passenger vehicles. A whole lot of back-to-base vehicles, other vehicle types, buses and the like, need to be configured for that. I see, as we progress, there's been a little bit of conversation. As a company, we see that networks are changing. We're seeing a whole lot of wind, solar, gas grid, power to gas options are being developed. I think that all things come into play that we can start and look at replenishment at a local level as well as a network-wide level in different ways. And courtesy of the discussions with South Australia, who are going to use their solar to liquid hydrogen and have already signed an MOU with Japan for supply of liquid hydrogen to Japan, That's another future that is perhaps not as far away as people might consider, and that will make a huge difference when we get to the future demand for supply at a local level and across a breadth of applications, not just transport, but stationary, backup power, portable power. Cities want clean air, and they can do it and need it, not just on transport, but also around building, construction, site, and the like. And that's where hydrogen and fuel cells also have a role and can play a significant, can achieve a significant impact in air quality in cities and also less noise. Thank you.